righty. Let me admit everybody. Da, 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 da. And all right, my screen.
And I disabled the waiting room for you.
Oh, thanks.
There's Asen.
Alrighty, now we made Michelle big so everybody can see Michelle. Hi, everybody. Welcome to the panel with our lovely guest, Michelle. Yay.
Hi.
So we'll just let you take it away, Michelle.
Okay. I know, I've been doing TagCon for a couple of years now, and we've sort of been having these sessions about ask a friendly astrophysicist. You can ask me any questions you have about what you've heard in science and the news recently, or things you've been wondering about. I do have some slides I could show you if you'd start discussion. But I think, what I always enjoy most are your questions. And, I can, I have images I can bring up. I have different topics I can tell you about, or we can start by saying, has anybody been wondering about something or heard anything in the news that they'd like to talk about? And I guess I don't know how you'd like to moderate the session, but if anybody has any questions to start with, we could start with that, or I could kind of take off on talking about some of the things that are going on at NASA. Does anybody?
That was our first question, Michelle. I think we had Nancy on the question.
What's going on at NASA?
I do have a couple of questions here.
Okay, all right. Well, sure. So let me start with just a little brief what's going on at NASA, and then maybe we can go to some of the questions. And then afterwards, if people run out of questions, I have my slides too. So it is an amazing time at NASA right now to be in the Science Mission Directorate. NASA is kind of divided up into the human spaceflight part and then the science part, which has all of the robotic spacecraft and the science experiments. The two definitely overlap. In fact, just yesterday, the astronauts that are going to be on Artemis 2, the mission that will go around the moon and back, we're at Goddard Space Flight Center. Everybody at Goddard turned out to see them. The auditorium was overflowing, and one of the astronauts, Christina Cook, was actually a former intern at Goddard, and then actually had an engineering job at Goddard before she went to become an astronaut. So it was kind of old home week for Christina, and that was really nice. So we're there's so many things going on right now. So just kind of thinking about some of the things that are at the top of my head. Certainly the Webb telescope has been performing even better than we expected. And the whole way that the Webb telescope worked is that the first year of observations. So Webb launched a year ago last Christmas time. It was actually Christmas morning a year ago. And And so we sort of had some very fast observations to do to kind of show that the observatory was working and kind of show a little bit of an idea of its capabilities. And then after that, people had already applied for time. Anybody is welcome to apply for time on the telescope. It's an open application. And so we'd already selected the first year of observations. And so we're basically working through those right now. And people get about 6 months to have the data to themselves to publish the papers, and make their official discoveries. And then after that, it goes into an archive where anybody can use it. It's basically at that point non-copyrighted. You can publish it, you can use it, you can do whatever you want. After 6 months, it belongs to the world. And so, we're sort of we have this kind of fire hose of results coming out because everybody now is getting their results out from the first year of observations. And they range from looking at the atmospheres of exoplanets to the farthest galaxies ever detected to I think a lot of people, although things like the exploding stars and young stars and a little bit of everything. I mean, it's a public observatory, so astronomers are allowed to use it to look at whatever their favorite topic is, and so that's all been going on. I know the thing that, big surprise. I mean, one of the big mysteries is how you get such large structures and particularly large black holes at such an early time in the universe. And we're now looking back with Webb, some of we actually found the farthest galaxy. This is kind of a funny story, and I may have told it last year, so pardon me if I had. That we actually found the first galaxy, the farthest galaxy yet seen.
Right.
When we were just testing out the camera. Did I tell you that last year?
Yeah.
So now we see it's like oh, there it is. Yeah. Yeah, so I mean, it's
We get new people here this year, so they didn't hear it last year.
okay. Well, so I mean, for those of you that weren't here last year, we were just sort of testing out the cameras to see that they were in focus and working. And we did, a relatively, a short exposure, a 3-hour exposure. We let the camera open up to the sky and look at the sky for about 3 hours. And of course, with the sensitivity of web, you see a lot of things in 3 hours.
So high
But
resolution. I was gonna say, it's amazing, right?
I know, yeah.
It's
I mean,
way bigger than Hubble, and
oh yes, way
Yeah.
deeper. And we can talk about why. I know we talked a little bit last year about why, but we can also reprise that as well. But just in the 3 hours, it's like we started the experiment, went to lunch, and came back, and there's the farthest galaxy ever seen. And and now that we've done some at least deeper exposures, we've gone nowhere near as deep as we're going to go out into the universe. But even with some deeper exposures, we're seeing things like many big galaxies way back in time, maybe when the universe was say 300 million years old. I mean, that's amazing, because 300 million years after the Big Bang, the universe was much denser. It was a smaller place. Dark matter was much more prevalent. Everything was just more smushed together. And we see giant galaxies merging together, probably to become the first big clusters of galaxies, forming some of these ancient supermassive black holes. And so we haven't answered the question yet of where do these giant black holes come from. But one of the things that we may be answering is about how they could exist is that when you just have two big black holes that are, say,
Right.
1 billion times the mass of the sun, they orbit around each other very slowly. There's a lot of mass there, and they have to lose orbital energy to actually spiral in and collide with each other. And these big behemoth things, one of the problems was, it should have taken like the age of the universe to do that. I mean, there hasn't been time for these big things to orbit around each other and actually dissipate energy so they can spiral in. Now we see multiple big black holes spiraling around each other, like 3 or 4. And that might help, because basically, instead of two sort of gently orbiting around each other, you're getting sort of these chaotic orbits, because they're all influencing each other. And if you throw out one of them, that's a great way to lose orbital momentum, angular momentum, and have these other things get closer together.
Michelle,
so,
did they eat each other? Would
Yes.
it be possible to do that?
That's right.
All these big ones, like they became so much bigger because they already ate another big one. So it's like they're just
So black holes are happy to eat anything, including
Right.
other black holes. Yeah,
Right.
I mean, anything with mass is going down a black hole. Dark matter, fine. Regular matter, fine. Antimatter, fine. And yes, they'll eat each other and then just become a combined black hole with that amount of mass together.
Right, right.
And so one of the big problems with these big black holes that formed only 200 million years after the Big Bang, and now we're seeing back to that time. We have telescopes sensitive enough to actually look so far away that we can see things at that distance that light took.
It's just amazing.
7 billion years to get to us. And so we're beginning to see the early universe organize itself. And we may have some, again, we're going to be looking deeper and better images over time, but we may have some idea now about how these big black holes may have formed, because right now, and we may be wrong, okay, right now the only way we know how to make a black hole is a giant star dies. We know of no other way the universe can make them. And this may turn out to be wrong. Okay, so this is the state of science today.
Wow.
We don't know any other way to make them. And so when you see a black hole with 1 billion times the mass of the sun, and you're looking at it so far away that you're looking at it when the universe was only 200 million years old, you go, how could there possibly have been time for billions of stars to live, die, explode, collapse into a big black hole? I mean, it just doesn't seem like you would have the time to do that. And then, like I said, you have black holes, you can make bigger black holes from smaller black holes, but it takes a long time for them to orbit around each other and collide. And so now we're seeing these giant million or billion solar mass black holes kind of all rotating around each other in the early universe. And that's probably some of the way that they were able to combine, was not just two of them, but a whole bundle of them together, kind of all pulling on each other. So we're now seeing so far back that we're watching that sort of very first organization. And the real holy grail for astronomers that study stars like me is to eventually try to find a star that is the first generation of stars. And again, I have some slides we can talk about this, but stars make all of the chemical elements in the universe besides hydrogen and helium. The universe just began with hydrogen and helium. And we're now looking at stars that are the first generation, maybe like the second generation. They have almost no elements except hydrogen and helium. But we want to find one that is nothing, no other chemistry but hydrogen and helium. And we think that stars might work very differently. And so we might be looking for stars that are gigantic, thousands of times the size of the sun, the mass of the sun. Yeah. And that may be one of the ways you get so much mass falling into black holes quickly, is this first generation of stars. The stars themselves may only have lived a couple thousand years, if they ever really stabilized at all. There could have been these big cores of matter rushing together, matter and dark matter. And they just basically made these bursts of fusion and then formed big black holes. So, there's all sorts of things we're trying to find way back in time with the Webb telescope now. Yeah.
That's amazing. What about Earth? What generation stars, sun, our sun? Is it like many, many generations later in the middle of the?
Yep. Yeah. Yep. So when you look at the surface of the sun has a little smattering of almost anything on the periodic table. And that's because the dust cloud that we formed out of, was enriched by dead stars exploding and creating this material. And in fact, I mean, if you'd like, would you like me to show you a little bit about my slides about that?
Yes, please.
Okay, all right, let's do that. So, and I want to leave a lot of time for questions. So this was actually, first let me share my screen. This was a presentation that I did for the month of Women's History Month. And it was funny because I was thinking yesterday about what all to talk to you about. And I realized that this presentation had a lot of the new discoveries, but also interestingly, how they're rooted back in the past, largely to discoveries that women made. And, I think that astronomy, it's one of the best sciences for the preservation, at least, of women's contributions. And so, I mean, this wasn't meant to be at all in any way exclusive, but I'd made this. I thought it was an interesting story about how all these things were rooted in women's observations. So let me.
So cool.
Oh, did somebody say something?
No, we're just saying that's really cool. That's
all right. So, all right. Let me share these slides. Can you see something that looks wonderfully spacey?
Oh, that's beautiful.
Yes, very spacey.
That's a real image. It's one of my favorites. It's from the Hubble Space Telescope, and not Webb, but Webb just hasn't had the time to take these huge images, because this is a mosaic of actually hundreds of images from Hubble, and Webb will do this too. In fact, the very first released Webb image was of this nebula, a very little part of it, because we haven't had time to do the whole thing yet, but we will. But the Carina Nebula is one of these clouds that I mentioned that is forming stars. And, at our time in the universe, this is local. This is only about 1,000 light years away. So it's relatively close. It's in our own galaxy. A light year is about 6 trillion miles, give or take. And so, the distance that light travels in 1 year is about 6 trillion miles. This image is probably at least, I would say, 20 light years across, maybe a little more. And it's full of dust and schmutz and stuff and gas. And all of that is the result of dead stars. When stars go through their lives, they create all of this debris, and then new stars form out of the debris. And so, we are a late generation star with a little bit of all the stuff that dead stars create. And this is actually my favorite thing to look at in the Southern Hemisphere through a small telescope. If you have a small telescope on a dark night, unfortunately in the Southern Hemisphere, this nebula is absolutely gorgeous. There's the largest star in the sky right over here. If you can see my little pointer, it's called Eta Carina. Eta Carina is 2 stars orbiting each other, and they're both about 70 times the mass of the sun. And we're not worried about many stars in the sky exploding. For the most part, that will just be a nice show. You know, if Betelgeuse, for example, ever does explode, which I hope it does, it'll be lovely. It'll be a beautiful, bright. I mean, there'll be a little sun in the sky for maybe a couple of weeks, and you can probably read by it at night. But it's no harm to us.
Oh my goodness, that's amazing.
Yeah. Oh yeah, yeah. Eta Carina over here is actually one we're a little worried about. Because these stars are huge, and they're close enough to us that if we're kind of in the way of that, the shock of that explosion, it could. I mean, it's one we're looking at. I mean, one of the. We'll talk a bit more about this in the presentation. One of the things that some people think limits the ages of civilizations is that there are enough of these giant stars that explode. And if you're sort of at the wrong angle, and we don't understand this very well, but if you're sort of in the wrong way of the explosion, one of these things could kill a planet all the way across the galaxy. And it may just be that, you know, all of us living are kind of biding our time until this happens. And unfortunately, there's no warning, because the dangerous radiation in the form of very high energy light travels at the speed of light. So there's no way to see it coming. It arrives at the speed of light. And so
it'll zap us out of existence.
yeah. And we wouldn't, it's like, oh, there goes our planet. Whoops. And you know, and so unfortunately, we wouldn't know anything until something had stripped our atmosphere off. And then we also have these new stars being born, this cluster of pink dots. Those are all baby stars, bigger than the sun. So I mean, this is not an exceptional place. I mean, the galaxy has many thousands and probably millions of clouds like this. And so, you know, this is where we come from, and this is where all of our biology comes from as well. The clouds make organic molecules in buckets full. I mean, every single molecule that goes into our DNA and RNA. So it's not that we have found DNA and RNA in space, but in meteorites, which are sort of the preservation of these clouds, bits of the cloud that kind of clump together and weren't ever made into anything larger like a planet. When meteorites come down and we analyze them, we have now found all of the nucleobases, pretty big organic molecules that make up RNA and DNA. And so, you know, our stellar origins are really very clear. That, you know, these clouds, you know, are the debris from exploded stars. Exploding stars are great at making carbon. For those of you that love silicon-based life form science fiction, it's not impossible. But I have to say, these stars make thousands of times more carbon than silicon. And while silicon is an atom that could possibly form bonds similar to carbon in our body, it may have happened somewhere in the universe, but when you have thousands of times more carbon, and carbon's even stickier than silicon to form great, you know, molecules, chances are life in our universe is carbon-based, just because of the way stars work. They're much better at making carbon than silicon. So, you know, that's you know, that's the origin of our biology. Yeah.
Michelle, sorry to interrupt, but what kind of a planet would require for a carbon-based life form? Would it be like a atmosphere of a carbon, or I mean?
Oh, we are carbon-based life forms.
I mean, sorry, I mean silicon.
Silicon-based life form. Yeah.
Right.
Yeah, you know, I don't know. This is something that, you know, I bet if you went to our astrobiology department at Goddard, and we do have an astrobiology department, I love that. I bet if you just got everybody around lunchtime and said, how could you possibly get a silicon-based life form? You know, I mean, yes, I know it's millions of times less likely, but in a huge universe, you know, what might that be? It might actually not look that different from us, because we don't bear a whole lot of resemblance to graphite or diamonds. And it's just that the atom carbon is great at sticking other things to it. And a similar atom is silicon. It's great. It has electrons that want to bond with other things. It's just the structure of the atom.
Maybe we'd be like rubber creatures.
Yeah. So I mean, you could have a silicon-based life form that looked like us, because all of our soft bits are things like hydrogen and water and sulfur and phosphates that glom onto the carbon. The underlying skeleton of our molecules is carbon, but we don't look like carbon. So, you know, I mean, silicon life forms don't have to look like rocks, just like we don't have to look like diamonds. they could be soft, squishy, watery things like us too, that just have silicon as the underlying backbone of their chemistry. Yeah, yeah, kind of neat.
That's just amazing.
And please ask questions, because I'm happy to have this discussion go any way we want it to go. So
Nancy,
yeah.
can you ask the one about the, I'm trying to think, there's an exoplanet one about the,
Yes, okay, I've got the questions
Okay,
here in
exoplanet,
front of
right.
me. There's been a recent discovery of a mini Neptune exoplanet or a gas dwarf, as opposed to a small rocky planet like Earth or Mars. We're used to thinking of gas giants, not little gas planets like that. What's the significance of that kind of planet to our understanding of what's out there in the universe?
Yeah, it's a wonderful question. And it's one of my favorite parts of the story of finding planets around other stars. And actually, I think in order to answer that, I actually saw, hold on a sec. I actually saw an animation the other day of finding planets around other stars, and I thought it was really nice. Let me play that. I'll share my screen. So, okay, that's in hold on a second.
things like the little gas things are so strange.
Yes, I know.
Like, Saturn, giants, these big gas giants.
You're right, absolutely. So yeah, here, hold on, let me share my screen, and I'll play this little thing for you. So one of the things that's happening is we are now finding planets around other stars in absolute scads. I mean, there's so many of them. So if you can see that animation, this is kind of a fun animation of looking at where we're finding all these planets. So right now we only find planets in our own galaxy. We don't really have the capability to find them in galaxies outside the Milky Way. So in this slide, you see the Milky Way as you would see it across the sky. When you see like a big band of light, on a really dark night, you can actually even see some of these dark clouds in the Milky Way that go right through the middle. Those are debris from exploded stars. The Milky Way is about 100,000 light years across, the disk of just our galaxy. So by the time you look even just to the other end of our galaxy, light has taken 100,000 years to get to you. And the galaxy is chocked full of this debris from the exploded stars. All of this smoky stuff is all dead stars that blew up and eventually become things like us. And so this kind of shows you the history of where we're finding exoplanets. So they have all these little detections. At first they came just a couple at a time.
Goodness, what is that?
And I just want to show you, I'll just pause it. There's a little bing for each exoplanet and all of that. And I think the reason this part of the sky is so absolutely full of exoplanet detections is this is the Kepler mission. The Kepler mission decided to just take a relatively small camera and stare at one part of the sky for years and not move. And in this one relatively small part of the sky, we found 500,000 planets, basically. It's wow. It's a lot, yeah. And we're still following up on a lot of them to see if we actually confirm them. Bing. So we now find about 1,000 planets a year around other stars, and the James Webb Space Telescope this is the first time, and we're doing this right now. We have the capability of actually finding out what their atmospheres are like. Do they have atmospheres? Are the atmospheres the same temperature as the Earth, the same chemistry? Are there any signs of life in the atmospheres? And yes, we have also had meetings at NASA. Are there any signs of technology? Any techno signatures? Yeah. So the person's question is an excellent one, because we're now finding these planets that they're usually about 5 to 8 times the mass of the Earth, and it looks like they have extended atmospheres similar to a little Neptune or a little Uranus, a little gas giant. And there are also a huge number of these planets where we only know the mass of the planet, but not really whether it's gaseous or solid. And it turns out that these are the most common planets found in our universe, are planets that are about 5 to 8 times the mass of the Earth. And they might either be big solid planets, You can think about people on a heavy world, people that perhaps creatures, I should say, that evolved in an environment where maybe you have 4 or 5 times the force of gravity. What would that be like? And then you also maybe have things like mini Neptunes. Maybe they're water worlds. When I think about the Star Wars universe, there are some planets that only have water, and they have like it's always raining. I mean, the thick atmosphere, water worlds, they may be like that. Some of them are close enough to their stars, they may be very hot, like little mini Jupiters inside. The thing that I just love is that when we go outside and look at the rest of the universe, we have no planet like that here in our solar system. We don't have anything that's in that mass range. We have the Earth, which is the most massive rocky planet, and then you go up to Neptune and Uranus. I mean, then they're the next step as far as mass goes. We don't have anything that's in that range, and so
are we strange? Are we a strange solar system?
yeah. Well, so that one of the questions is why, and one could just be luck of the draw. Different solar systems happen to form different planets. But the other really intriguing thing is that for the first time now, and I'll stop share. For the first time now, we understand how much our solar system has changed. And we didn't know this until, when I started working at NASA, we didn't know this. So I've been working at NASA for about 26 years now. And one of our deputy head of astrophysics, he's a great guy named Avi Bendel. And Avi was one of the authors on the paper where they began to suspect that Jupiter had done some pretty mischievous things in the past. And we had started 20 years ago running supercomputer simulations of how gas would come together to form planets, and everything's moving around a young star. And so we were doing, we have a computer at Goddard that does it's up to 8 petaflops, which I think is I think that's like 8,000 trillion operations per second. I mean, it's amazing. And we noticed that as planets form, they gravitationally tug on each other quite a bit. And in fact, if you have 2 planets that are the size of Jupiter, they basically disrupt all the other planets and throw things out willy-nilly. So some of it goes into the sun, some of it goes out into space.
Right.
And we've seen that. We've seen planets careening around the universe that are not attached to a star. And we think that's probably what happened because they're moving fast. It's like something gravitationally slingshot them out. Yeah, and
like a slingshot, right?
That's right. That's right. Yeah, and so one possibility is that we had other planets, and when Jupiter was busy tugging on everything, it threw some of them out. And then there's now something called the migration of Jupiter, or it's actually called the grand tack hypothesis. And when they say tack, it's the sailing term, tacking against the wind. Because we now have increasing evidence that in the early solar system, Jupiter moved into about the orbit of Mars. And we think it completely disrupted, any other planets forming there. It probably threw in most of the asteroid belt towards us. The asteroid belt right now does not have much stuff in it. If you put all the asteroids together, it wouldn't be much more than the mass of our moon. And so it also, when you look at the surface of our moon, you see all these huge craters, and they seem to have come in a couple of waves. And of course, all that stuff hit the Earth too, and probably all the inner solar system. And so when Jupiter was moving in towards Mars, it just disrupted all the inner solar system. Good for us. It probably brought the water that is on Earth and in our bodies right now. That probably came from the outer solar system as Jupiter dragged things like asteroids and comets in. So it was a violent time, but it was a time we needed for the beginning of life. And so we now have evidence in many different ways that Jupiter did this. And so it's possible that we had one of these super Earth mini Neptune planets, but it got flung out. And one thing that kind of piques my curiosity as a scientist is that the stuff that we're finding way outside of Pluto, the very, very outer solar system, you may have heard this. Everything is lined up in orbits that are too ordered to really be chance. And it almost seems like every, let's say, million years or so, maybe a larger object swings by and kind of gravitationally organizes everything out there. And so that has us wondering if Jupiter threw one of these super Earth planets out, it could still be in a very long orbit around the sun. Yeah.
So beyond Pluto, like another planet that's way beyond.
Yeah, but judging from how these, this is conjectural, but judging from how these outer solar system objects are all put on this beautiful plane together, it would have to be bigger than Pluto. It would have to be bigger than the Earth. So, I mean, maybe that is our super Earth that got swung around back there. It's an interesting idea because, I mean, if that planet were in its long part of the orbit, we wouldn't be able to see it. It would just be too small and too dim in visible light. There are lots and lots of people looking for it in infrared surveys of the sky, heat surveys of the sky, but we haven't found it yet. So it's an interesting idea. Yeah. So that's, so the question about, what are these planets like? We don't know. We don't know whether some of them might be big solid planets. Some of them might be smaller gas planets. And some of them may be like water planets, a place where you have nothing but water and no land. So, I mean, it's a fantastic idea to think of what they might be like. Yeah. Is there
Michelle, you mentioned Artemis and the moon. Now, my age, and this is actually a question from Liz. We watched in 1969. We watched those first steps on the moon. The video was a grainy black and white television.
That's right.
And it was, we could barely see what was going on, and if the light wasn't good. Now Liz remembers being proud of the Parks radio.
Yes.
Because she lived in Australia.
Yep. I've been to Tidbinbilla, so the Tidbinbilla tracking station, as well as the Parks radio are, that's a big deal.
But the images we're receiving now from the James Webb Telescope are in color. They're much clearer. Do you think the clearer images will create a bigger impact for the public?
Well, it certainly would be lovely. I imagine, I don't actually know, and I should find out exactly what sort of cameras they have on this Artemis 2 mission, because they'll be orbiting pretty close to the moon as they go around, and so I mean, hopefully we'll have spectacular images. It'll somewhat depend on exactly what phase of the moon is in, and because we don't have a launch date yet, we don't know that yet. But the thing that to me has always been tragic about lunar science is that basically for political reasons, the moon has kind of been earmarked as we're going to leave that for astronauts to explore. And that's wonderful. I mean, I think that's great. But the problem is a lunar mission is incredibly costly. I think a lot of people never realized quite how much was spent on Apollo in the 1960s when it was a big political stunt to basically show Russia that we had intercontinental cruise missiles. I mean, that really was why we did Apollo. And so we had these huge missiles that we were putting people on, and we weren't like, it wasn't an act of war because, hey, we're going to the moon, we're okay, we're not trying to hurt anybody. But that really was the purpose, and the purpose was to show Russia what we had rocket wise. And we, for a time, had those being built on something similar to what the military's budget is today. And to give you a sense, the NASA, the science side that I work on, we have 110 operational missions, things from the $10 billion Webb telescope to the Mars rovers, to smaller satellites, to Earth satellites, to things that monitor the sun for solar outbursts. We have a wonderful spacecraft that's orbiting the sun right now at 450,000 miles an hour, fastest human-made thing ever. But all of that part of NASA, last year, the Pentagon spent more on air conditioning.
Ooh.
So to give you a sense of our budget.
The generals had to stay cool.
The Pentagon spent more on air conditioning last year than our entire science budget. And the human spaceflight program is much, much more expensive and much more vulnerable to people saying, well, I mean, we've been saying we're going back to the moon since George W. Bush, or actually, no, his father, George Bush. And nobody really wants to pony up the funds. And so, while I really hope we do see astronauts back on the moon, just because of the political football that's being played in terms of the funding, And also the fact that a lot of people don't know, Elon Musk has the contract to do the lunar lander. So, NASA can't go to the moon until Elon finishes the lander. And he has a way of going squirrel, and doing something else. So,
well, I do remember, and this was on a personal level, the motor that was on the lunar vehicles was created, I guess is the best word, built by the company where my dad worked. Yes, it was an electric company. They made motors.
Yep.
And, Dad was quite, proud of that. And when the moon rocks first came to us here at our planetarium, back in the days when you walked through with your hands behind your back because you couldn't touch anything. I mean, it was quite a big deal. Oh, yeah, okay, well, that's fine. They're little black rocks.
Well, but see, I mean, it's funny. It's funny how topics all lead to each other. I mean, for those of you that like, Douglas Adams and, who's the detective that,
the Hitchhiker's Guide.
Yeah, the idea that you can investigate anything in the universe that will lead to every other thing in the universe. Yeah. It was the moon rocks that got us on that kick about what happened to Jupiter, because the moon rocks were totally unlike anything we expected. We expected them to be either very much like the Earth, if the moon had formed kind of along with the Earth at the same time, or maybe very unlike the Earth, if the moon was some object that was captured somehow and started to orbit the Earth. But again, the universe said, ha ha, neither one. They were like the Earth in significant ways that this object couldn't have formed very far away from the Earth. And at the same time, everything that you could possibly burn, anything that's volatile, anything that's light, was absent from the moon rocks. And the only rock that would behave that way is if something was basically the product of a huge explosion, a huge energetic event that had blasted away all of the light stuff, but the other stuff remaining was very similar to the Earth. I mean, atom by atom, we looked at things like isotopes, the number of neutrons in each atom, and this stuff was very much like Earth material, but it'd been exploded. And so that gave us the first path, and now there's more evidence that the moon is the product of a collision between the Earth and another planet. And these two planets collided. There was probably a ring for a little while, and then that ring gravitationally organized into the moon. And now there's more and more evidence for that. And so when then you ask yourself, well, why was there another planet colliding, coming right toward us? We think Jupiter was busy throwing stuff around now.
And that's why. Okay.
Jupiter was just being a bad boy.
Yeah. Well, I mean, so you say bad boy, and at the same time, I'm very quick to tell people that when we look at stars forming in other parts of the galaxy, planets that are as close as we are to the sun don't have any water or moisture or anything that makes soft creatures like us. And so, we really do think that event created the conditions necessary for life. Jupiter comes roaming around. All this stuff gravitationally gets drawn in from the outer solar system, where you have so much more ice. We have whole worlds made of ice in the outer solar system. And, asteroids are full of water. Even the rock on asteroids have water dissolved in them. Some asteroids even have little inclusions of ancient liquid water. Amazing.
Oh, cool.
And so all this stuff gets thrown down. And this is one of the reasons why we want to sample asteroid material. So another big thing that's happening at NASA is the US's the world's first big sample of pristine asteroid material is coming back on September 24th, I think. Ooh. And that's part of the OSIRIS-REx mission. I was the host for that. Boy, was that I think that was 2020 or 2021. I think it was 2020. Yeah. And takes a little while to get back from an asteroid. And we picked up hopefully a couple kilograms of asteroid material that is unaltered since the beginning of the solar system. Unlike meteorites, that's our usual way to sample asteroids. It hasn't been burning through the atmosphere and then sitting on the ground for God knows how long. So we actually went up to get this very pure sample of asteroid material. We already know it's full of organic molecules, full of the stuff that we're made of. And so you let organic molecules, which dead stars make, fall down from the sky. Jupiter sloshes us in with a lot of water. and you let the thing sit for 4 billion years, and hey, here we are. So that's how we're piecing this all together. And so the moon rocks led to us completely rewriting the beginning of the solar system's history. And that led us say, well, let's get a sample of what we were like prebiotically. I am not being overly dramatic. When we bring back these asteroid samples, that's us. That's the material that made us, but it just wasn't altered since 4 billion years ago.
Wow.
So, yeah. So
another kind of general question. This again came from Liz. She said she finds it strange the headlines tout, the first woman or the first person of color. Are these labels really important? And then, having spent 30 years as a Boy Scout leader, I know the original 12 astronauts were all Eagle Scouts.
Yes.
And so why do we need the labels? I mean, why can't we just base it on their knowledge, their skills?
Mhm.
And we have to make a big deal out of race and gender, and
So
because in our tag universe, we're not like, it's not like that. Everybody's kind of, it's based on merit.
absolutely. There's a couple different answers for that. And, I think this is one of the things that I kind of got educated about. To me, gender has been nothing but a disaster. I mean, I've never felt in any way traditionally feminine. I mean, I happen to be what they would call a cisgender heterosexual female. I've always chosen sexual partners that were men, but the whole idea of just not being a human being, let's just be humans with whatever genitalia you happen to have, and we have different interests. And so for me, I was always very attracted to a genderless society. I mean, I would love to use the pronoun they, just for no other reason than I don't feel like a she. I just feel like a human. But then one of my friends, who is a prominent astronomer at the American Museum of Natural History in New York, and she also was on a National Geographic article, a whole issue that was dedicated to the idea of gender. So she's a trans woman, and she doesn't even like the word trans woman. She's a woman. She transitioned gender. When I first started working with her, I knew her as a man, and now I work with her as a woman. And when I was sort of talking to her about, well, what does it really matter? Wouldn't it be better, if we just said we're all just human, and wouldn't that make it easier for you? And she talked about how hard she had fought for, the recognition of her gender and her identity. And, she didn't feel like a they, she is a she. And so I think in any given population, we're not going to reach agreement on how gender should be handled. And I think allowing that grace with each other to be, I assumed that being genderless would be something my friend would want. And I was wrong. And it's the same thing with my friends of color. There are some of my friends who say, I would love it if nobody even noticed. And then there are others that say, I have fought hard for my identity as a person of color.
Yeah.
So, it's one of these things that yes, I would like to live in a society where nobody even thought about such things. The 4 people that were picked for the crew, a white woman, an African-American man, and 2 white men, are by far the best 4 people for that team. In no sense of the way were they picked that way, for specifically. I mean, yes, they wanted to have a crew that was more representative of people, and in terms of color and gender. And I completely, again, I think we need to give each other grace. The person who asks the question, their idea is like, isn't that not the right way to go? I have sympathy for both sides of the equation. I mean, I think if we had picked 4 white men, there would have been hell to pay.
Yes,
And
I would agree with you there.
And but the people are spectacular. I mean, while I am sometimes not much of a political supporter of human spaceflight because of the cost, and because I think people use it politically and they're never going to let us do it, the astronauts I know are the best people I know. I mean, they are no longer these sort of swaggering fighter pilot, cocky types. They are nothing like that. They're the best people in the world. And it's funny you should mention that, because Christina was part of, here's an interesting thing. Christina was part of the very first spacewalk that involved
That's right. Yes, yes.
two astronauts, and then the commander on the ground was also a woman. And NASA did not plan that. We did not announce it. We didn't plan it. We just had the astronauts were on the space station working with whoever the director was at the time. We didn't do that deliberately. We did that with no, we didn't care. We had the two specialist astronauts who were the people we needed up on the space station. We had the person that was on rotation to be the director that day. We did not engineer that. And then all of a sudden the press sort of looked and said, hey, wait a minute, all of these people are women. And it became this sort of, media thing. And when we were looking at each other going, and then it had to be put off for a little while because there was a problem with one spacesuit, and then everybody got upset and all of that. But, at NASA, we had not engineered that. Those were just the people who were up at the space station and the people who were on duty at the time.
So do you think perhaps the media has more to say than the actual people that do the job?
NASA needs to get better at building groups that are more representative of human beings. And going back to, it's funny, all the way back again to the first thing I talked about, but the James Webb Space Telescope's first year of observations. For the first time at NASA, I don't know if it's been done elsewhere, but for the first time at NASA, for the James Webb Space Telescope, we decided to evaluate people's proposals as to what they wanted to use the telescope for. It's like, I need, 90 seconds to look at this star, and I want an hour to look at this galaxy. We took all of the identifying names off, all of it. And that created a bit of an outcry in the scientific community, because there are people who are excellent established astronomers that, wanted their name. Look, I've been working with space telescopes for 20 years. I'm really good with this stuff. My name should be on there. And we made the decision, popular or not, to take all identifiers off. Just look at the proposal science. And
we do have, Ellen is saying she agrees with you so much. She is a female engineer, and she so often had to ask herself if she merited the opportunities she had, or if she had them because she was a woman.
Right. Say that again, but let me just finish this bit. And
okay.
Because what I'll say is that the first year after we took everybody's names off, whether they liked it or not, we have by far the most diverse cohort of people using a space telescope that has ever happened, and diverse in many ways. Certainly diversity in gender. Very much more than any other space telescope observing time. Definitely diverse in ethnicity, meaning color and also economic background. But here's the interesting thing: a really interesting diversity as in young scientists versus older scientists. A lot of older scientists were hoping that, hey, me, I have a Nobel Prize, give me time, and they didn't write as good proposals as the young scientists did. And so we actually have, for the first time, a class of people using astronomers that is much more representative of people around the world. So, there are ways we're trying to identify this, but one of the reasons we're doing stuff like that is because we look at our numbers and they're terrible. When you look at the number of people who are not white men that are leading NASA missions, yes, it's getting better, but wow, is it not getting better fast enough? Given the statistics of how many women astronomers there are, how many astronomers of color there are, or whatever, we are still over selecting white men, even with wonderfully qualified people who are not white men. And so, by the way, I love white men. My husband, I'm a huge fan. I watched my husband, as who tragically passed a couple years ago. He being a good engineer at NASA, he got put into jobs for every next mission without even interviewing for them. They'd say, "Oh, Andrew, I know Andrew. He's a great guy. We worked with him really well on the last mission." And then they would just hire him, into these senior positions.
Right.
And every woman I know, including myself, that's never happened to me. I always go and interview with the pool of candidates. And I thought that was how everybody did it. And then I was married to a very brilliant white male engineer, and I realized he didn't do it that way.
That is a double standard there.
Definitely a double standard.
Yes,
Susan,
we're trying, yeah.
Susan, you've got your hand up.
Yeah.
So,
And I didn't hear all of that last question either. So
okay, the last one was from Ellen, who is a female engineer.
right.
She said she so often had to ask herself if she merited the opportunities that she had, or if she had them because she was a woman.
Yeah, to tell you the truth, if I can just answer for the world, absolutely you merited the accomplishments that you had. The only thing that I see are people being ignored more than they should be. I do not see people being given opportunities that they didn't deserve. I don't. I mean, there's kind of a I mean, I know, I mean, we talked a bit about imposter syndrome last time, and I have it too, but it's absolutely true. Somebody said, well, where are all the mediocre women? Because honestly, I mean, you get senior managers at NASA sometime that just, I mean, God love them, but they're not all that good. And usually you don't find mediocre women. You find really, really good women and mediocre white guys. So I feel the same way. I wonder myself, did I get this job or this position because I was a woman? I think we all carry that. But I also, when I look at my career in kind of sort of an objective way, and I'll be probably formally retiring from NASA in about a year. When I look back on it, I think I should have gotten farther than I did based on how my male colleagues did. So yeah, I think we could have them even.
Ellen also adds that her husband, who is also an engineer, has explicitly had selection difficulties because of his white male demographic.
Yeah, and so that's something as well that they say. And I sympathize. I really wish that we were in a culture that gave no beans about what we call gender and ethnicity. And like I said, I mean, human beings, skin tone, genitalia, these are really literally skin deep things. And how we've organized ourselves that way is tragic. There may be some of that. I mean, certainly as I see young scientists coming up, we have wonderful, wonderful young white men coming up as well. And it's unfortunate that anybody feels they're being left out.
I've got someone, Susan, you had a question.
Yeah.
Did you want to?
Well, no, I just wanted to add to when women, because my grandmother and great aunt in professions got PhDs at a time when women didn't get PhDs. And if you did, you were part of a quota. There was, and that in and of itself created the image that you were only going to see so many different faces. There's so many different voices.
Yeah.
People of poverty weren't given the education. They weren't given the mentoring. And I think that's continued a little bit. I always think of it as the golf club, the golf course theory. If you play golf, you have a better chance of going, getting promoted just because you know the person better.
That's so true. And that's part of why I really, when I work with my interns, we talk a lot about social networking and, and getting to know people and then if they know you. And in the case of, like I said, with my husband, it's like, oh, we know him. He's just like us. The mission that he was working on, he also spent time to mentor some younger women in that same mission who did not feel welcome. So this idea that, the white male scientists, not meaning to do any harm, feel very comfortable working with other white male scientists. And here comes along some people from different cultures, people from different countries, people that from different genders, different gender affiliations, trans people, all of that. And for some reason that they're not really thinking about, they just feel a little bit less comfortable with them. And when they're in that sort of gut reaction as to who to hire, you know, it's like, I really feel good with this person. I mean, these people, I feel for them, because we've had some hard meetings at NASA where these wonderful men and scientific mentors of mine would say, look, I select blind to gender and to ethnicity. I find the best people, the people I think will be great team members, and I am not looking at their gender or their color. And then we do the math. And we say, but look at the statistics. You know, even in a world now where you have many candidates that are women of different ethnicities, you are statistically over-selecting white men.
There's the
Still.
saying that there has never been a meritocracy.
Yes. No, there
And
hasn't.
it's an illusion and a dream.
Yeah, I mean, it was funny, I was giving a talk to some people in New York 2 days ago, and they were doing the thing that I really don't like, where they were talking about how brilliant I must be. You know, I'd given them a nice astronomy talk, it was fun. And they're like, oh my God, I mean, you're such a freak of nature. I mean, how is it that, you know, a woman can do this? And they weren't trying to say that. But, you know, I said to them, I said, look, you know, a single mother immigrant that just crossed the border from El Salvador and is working 3 jobs and trying to survive, not knowing the language, is far more brilliant and far more hardworking than I am. You know, I mean, this idea we have of, you know, in my case, I wasn't economically privileged. I come from a pretty poor family. I've been working outside the home since I was 12. But my parents were immigrants that valued education. And so, you know, what happened was, even though we didn't have any money, they were like taking me to museums, and they were taking me to guest lectures at colleges. And they instilled this idea in me that this was something good that I should be doing. You know,
exactly. Immigrants who valued education, no
Yep.
money, but
right.
everything for study, education, that's number one.
And I had the white privilege as well. But I mean, you know, seriously, I mean, who do you think is really having to use their brains right now? It's not astrophysicists. I mean, I love astrophysics, but you know, when you talk about poverty and meritocracy, no, I mean, this is the thing. How many Einsteins are working in fields now as migrant laborers? And, you know, how many people with absolutely brilliant minds for astrophysics, you know, died in the war in Sudan? And, you know, I mean, this is something as a civilization, you know, eventually, you know, we're going to, I don't know if we'll ever come to terms with it. But you were talking about women getting PhDs. Let me show you quickly, and I'm actually not going to go through the whole talk, but I want to just give you the narrative of some of these women that I was talking about. So let me just call that up, and then we'll go back to questions after that. So, because I think that the questions are always the most important thing. So let's see, presentations, and what was the one called Women? Let's go to recent. Exoplanets, women, there we go. Okay, let me just share my screen. I'll just kind of show you some of the, because I think a lot of times we don't even know what our past includes. So share screen. I'm in the Chesapeake Bay. It's a little hot and humid today. If I look a little sweaty, don't worry about it. I'm perfectly comfortable. I'm just a little bit warm. Okay, so let me just show you a little bit. So, and I won't have time to go into this whole presentation, but I think I'll have time to talk about a bit of the history that we may not be aware of. One of the things I was going to talk about, and I know I talked about last time, were neutron stars. And you know, these are the collapsed cores of dead stars. And this is an artist's conception, just to show you the size, the scale. They're about 20 miles across. And this is a neutron star compared to Manhattan. So you can see,
Oh my God.
you can see Central Park and all that. A neutron star has about twice the mass of the sun. And it's compressed into a ball about 20 miles wide. And these are real. We study thousands of these in the sky. And in the last couple of years, and for those of you that were here for, I think, for my last year's presentation, we went more into detail about some of the ways we observe these stars. They are incredible because the gravity around these things, think about that, 2 times the mass of the sun in 20 miles. The gravity actually warps space and time around it in a way that we can see in front of our eyes. When we look at these objects, we can see behind them as well as in front. because the light is curving around this hyper space-time warp, this gravity warp. And so, you know, the idea that space and time warps, these are not conjectural. We see them. And when we look at neutron stars, we can like, we actually have to do all these little algorithms about, don't get confused, that's the back versus the front and all of that. But the neutron stars really were largely discovered by a woman graduate student named Jocelyn Bell back in the late 60s. And Jocelyn Bell was the first human to actually observe a neutron star and to realize what it was. There were physics predictions that these things might exist, but nobody'd seen one. And Jocelyn Bell observed one when she was a graduate student and published the paper. And then the paper was accepted. Everybody thought it was a really good paper. And some of her early observations there. Like I said, I won't have time to do all of it. But the thing about Jocelyn Bell was that the excuse they used that was because she was a graduate student, she shouldn't get the Nobel Prize, that the Nobel Prize should go to her faculty advisors, who were men. And they did. They got the Nobel Prize. And this law about you have to be a graduate student didn't exist before Jocelyn. Other graduate students had gotten the Nobel Prize before and after.
Oh, that is ridiculous. That is.
So Jocelyn Bell is well known in astronomy today. She's still alive. Everybody, you know, she's just gotten every other honor they could give her. But because, I mean, she can't get the Nobel Prize for her discovery because other people already got the Nobel Prize for that discovery. And so you know, that's one of the things that I was talking about. So some of the most extreme and weird things in the universe that warp space and time were discovered by a young woman astronomer graduate student. And so we observe them. This is the satellite we have on the space station where we observe many of them. And I can leave some links in the chat for some movies about what these look like, you know, about how we observe the space time warping. It's all pretty amazing. But what I was talking about in my talk about women in science was that okay, I'm gonna do one thing, just so you know. These neutron stars, by the way, are hellaciously dangerous. I mean, 2 times the mass of the sun in 20 miles. Just think what's going to happen. And in 2004, there was a neutron star that actually had a tiny little. We think basically the crust of it probably shifted a centimeter or something, a tiny little shift in it. And that neutron star was, it was 50,000 light years away, halfway across the galaxy. 50,000 years ago, this neutron star compressed a tiny little bit. And it basically, in 200 milliseconds, you can see by my cursor, more energy was released than the sun creates in 250 million years. And the reason we knew about it is because it blew off the top of our atmosphere. I mean, we were fine, but it was a strafing blow. It wasn't a direct blow. And it basically fried a couple of our satellites, and the whole magnetic field of the Earth was ringing, and significant gas was peeled off the atmosphere. So again, these things are worth looking at. They may limit civilization age. But the thing though is that people don't realize the huge history of women in astronomy, particularly in the United States. And I went to Harvard University, and so I knew about these people because they were sort of part of our, undergraduate training, but so many people didn't. Harvard had a very, very active and rare department that welcomed women. In some cases as students and professors, and in a lot of cases, I mean, similar to the movie Hidden Figures, they welcomed them as computers, people that did the math and did the observations, even though the professors were the ones lecturing and actually publishing the results. But some of the most amazing discoveries that we have come down to this group of women. And so the original origin of this group of women was the head of the Harvard Observatory named Pickering back in the late 1890s. This was the time that we were starting to have big telescopes like the Yerkes Observatory, which had a 40-inch lens. And we were finally able to take very detailed pictures of the night sky with far more stars than we'd ever seen before. He had his graduate students looking through these big glass photographic plates and counting all the little stars on the plate. And they didn't do a very good job. And he said, my Scottish maid would do better than you at this. And so he hired her. He hired a Scottish maid to start this group of women that were combing through these observations, the first big telescope observations of the sky. And this is what a photographic plate would look like. It's a reverse exposure. So wherever there was a light on the sky, it made a little dark dot on the emulsion, the chemical emulsion on the glass plate. So this is, I think, a picture of maybe one of the Magellanic Clouds. And there are in this image tens of thousands of things to classify. And so the women were going through, and they hired usually seamstresses that were very good at doing detail work. And they went through and they classified all these stars. And here's a picture of one of the plates where they're busy labeling them all, and then they made catalogs, they made maps of the sky, but they also made some incredibly significant discoveries. And so you see here the women working through those glass plates, and you can read about this in a book by Davis Sobel that came out just a few years ago called The Glass Universe. And the glass refers to the big photographic plates, the glass plates that they were looking at. But there was a woman named Henrietta Leavitt, and Henrietta Leavitt was educated. She was somebody that had actually gone to school, had studied physics, didn't know how to get a job at the time. So Harvard hired her, I think originally sort of to do this calculation work, but eventually they did hire her on as a professor, and they hired her on as a scientist. And she has her own story about fighting for salary increases and all of that. But Henrietta Leavitt, looking at these plates, realized that there were some stars where if they had big telescopes take a picture of the sky and then a year later take a picture of the same part of the sky, the stars had changed. They weren't the same brightness. And in fact, she noted here VAR for variable. There's a star here that's different than it was last year. And she found out that stars change brightness. And specifically, she found a class of star that turns out to be the reason we know how far away those Webb telescope galaxies, billions of years in the past, are. She found something called a Cepheid variable star. A Cepheid variable star is a star that's about to die, and it's getting unstable. And it starts to basically kind of wobble. It starts to get brighter and darker and brighter and darker and brighter and darker. And the period, the time it takes for the star to get brighter and darker is actually correlated. It's directly related to how bright the star really is. So you can have a really bright Cepheid variable star. It's going to vary kind of fast. And then you can have the same star, but less bright. It'll vary kind of slowly. And so they had a way of saying they knew the exact brightness of that star. Looking at these variations, they could say, aha, that star is exactly that bright. And so now they had something called a standard candle. And that's an astronomy term we still use. It means that you have a candle, or I usually say light bulb to my class, and you know how bright that really is. That's a 100-watt light bulb. I know that.
Right.
And so if you see it really far away, you can measure the brightness. You're not getting much light from it. But the reason you're not getting much light from it is because of the distance. And light drops off, by the distance squared. And so she had discovered a class of stars that you could calibrate distance with. And she started to discover these stars in other galaxies. She's the first person that could actually say how far away other galaxies were. And she did that from combing through all these plates. And then there's another technique. So that they put the light, before it hit the glass plate, they put it through a prism, and they basically broke it down into a rainbow. Let me show that again. It's important. This is called a spectrum. The technique is called spectroscopy. You put the light through a prism, and instead of little dots, now you have all little rainbows on the plate. And it turns out that the rainbow will be, come here, let's pause at exactly the right time. There, maybe back a little bit. There we go. Okay, we'll pause it right there. The rainbow turns out to have different amounts of light in different colors. You don't just get a rainbow with all the light equal. Green's a little brighter than red's a little brighter than blue. And these changes in the light of the rainbow have to do with atoms, which atoms are actually present in the star. And that's how we know what the sun is made of. We know that there are, all these atoms that have these little fingerprints in the light. And every chemical element has its own special rainbow. Everyone does it a little differently, because the light that a certain gas will emit has to do with actually what the atoms are like. They're protons and electrons. They're all different. Each atom is different. And so each atom has a fingerprint that you can see on the sky. If you just take starlight and put it through a prism and make a rainbow, and you see where there's more and less light, and you go, oh, that's hydrogen. That's oxygen. That carbon, that stars became carbon.
This is so great, Michelle. I was going to say thank you so much, because this actually really helps with what I'm working on right now in
Right.
my story. So this is great.
Yeah. So, by the way, these women discovered an element that had never been discovered before, and it's on this chart. Does anybody know what element we didn't know about until the 1890s?
Helium, oxygen.
Helium. Helium had never been seen on Earth.
I was about to say helium, but I was on mute.
Yep,
Sorry.
yep. So no. So the reason helium comes from the word Helios, the god of the sun.
Right.
And helium was something that they saw this pattern. They saw this pattern of rainbow in some of the gas on the sun. But we'd never seen helium on Earth, because think about it. I mean, every time you have helium, like in a natural gas area, I mean, helium is lighter than air. It's leaving. It just goes right up off the Earth. It escapes into space. And so helium was discovered on the sun before we knew about it here. And then we knew to look for it here. But these women discovered helium as well. And now we know this is the periodic table. Every element has its own special rainbow fingerprint in the light. And so that's how we know the stars are made of things. So Annie jumped canon here with Henrietta Leavitt. So here's Henrietta Leavitt, and here's her colleague Annie. Annie started to classify stars based on how much of different gases they had from this rainbow. Do we have a lot of oxygen? Do we have a lot of nitrogen? Do we have a lot of hydrogen? And so she was the first person that began to figure out what chemical elements are in stars. And so there's Annie working again on one of these glass plates, and we're almost done. So this is what they look like. They didn't look like nice little rainbows. They basically look like streaks of black, but these patterns of lines are the same as those patterns of bright lines for each element. So there's each element has its own little signature, its little fingerprint, and the spacings of that light are different for every atom. And so she's going through there and she's finding out what patterns of lines there are. Seamstresses, they're amazing.
That's amazing to do this by hand, not a computer. That's just,
yeah, I know. Yeah.
incredible.
And here's where the story is. There's just two more women, and I think here's where it gets amazing, because the sun has a little bit of everything in its atmosphere. It's got a little iron, it's got a little gold, it's got a little bit of this, a little bit of that, and like I said, that's because we formed from a cloud that a lot of stars had blown up in, and there was a little dusting of everything around. And so at the turn of the century, in the 1920s, the prevailing idea of what the sun was a big rock like the Earth, because it had a little iron in it, had a little bit of gold in it, had a little bit of this, a little bit of that, had a little bit of everything the Earth has. And if you had a rock that big, that massive, it would glow. Just the compression of gravity. I mean, if you had a rock the size of the sun, it would glow. Just from everything compressing together under gravity would keep it warm. And in fact, Charles Darwin was at the time, people were saying the Earth was only a couple thousand years old. And Charles Darwin was looking at the Grand Canyon and saying, I don't think that would form in a couple thousand years. And when they realized the sun was a big rock that was just kept hot from gravity, all of a sudden there was more time. The Earth could be millions of years old. The rock would stay hot for millions of years. And Darwin was on record at the time, still kind of upset, because he thought this stuff probably took more than millions of years. When he saw the evidence of things like, giant valleys and mountains, he thought maybe it would take even longer. So along comes a young student named Cecilia Payne. Cecilia Payne came to Harvard. She was English. She wanted to go to the University of Cambridge, but they wouldn't let her in. And Cecilia Payne, as a graduate student, started looking at these lines, these spectral lines. And while, yes, you see a little bit of everything, this is actually the spectrum of the sun. That this is all of the little rainbows superimposed on top of each other. And each of these dark lines is one of those little fingerprints of an element. It's amazing. So we can see all of the different elements that are in the sun, just a little bit, tiny little bit. But she noticed that the lines for hydrogen and helium too were much stronger. So there's some like tiny little lines, maybe that's, a little bit of silver, but then there were other lines that were really big. And those were the lines of hydrogen and helium. And she said, well, if these lines, basically there's so much more stuff there that's hydrogen, helium. She, as a graduate student in her dissertation, said the sun must be made of hydrogen. and mostly hydrogen and helium. It must be a big ball of gas that's kept warm at some point. They didn't know about nuclear fusion. And the advisors, her male advisors, kind of laughed at it, but they only laughed at it seriously for a couple of months. And then they looked at the data and they did some experiments in the lab, and they realized she had to be right. And so Cecilia Payne was the person that discovered what stars were made of, how far away galaxies are, what stars are made of. These were contributions of women. And, the weirdest objects in the sky, neutron stars. And I'll just end, this is Cecilia Payne. Cecilia Payne was made a full professor at Harvard University. And she eventually became chair of the department at Harvard. And I'll just end with a woman who we're honoring right now. And I had a chance to meet before she passed about 3 years ago. And that's Nancy Grace Roman, another person people don't really know about. Nancy Grace Roman in 1958 was NASA's first head of astrophysics, first head of science. She was a brilliant astronomer who was at the University of Chicago, but they refused to give her tenure because she was a woman. And so she got a job at NASA as the leader in science. I mean, no figurehead. She was the leader. And she was the first person that came up with the idea of putting telescopes in space. Working for NASA, she was the person that said, well, if we put a telescope up above the atmosphere, we'd have a much clearer view of space. Different kinds of light wouldn't be absorbed by the atmosphere. And so from the 1960s on, this is the person that came up with the idea of space telescopes, Hubble, Webb, everything. And
So
our next big space telescope is going to be named the Nancy Grace Roman Space Telescope. Yeah.
All right.
All right, I'll stop there. We can go back to questions. Hold on a sec.
That was wonderful.
Yeah, so I mean, owning our own history, there's so much of this going on. I mean, now they're looking at Viking burials and realizing that, a lot of the Viking warriors were women. I mean, they just never looked at the pelvises before. Seriously. And if we were to go back in ancient time, I think we would be shocked. I mean, it's not that things were ever equal. I mean, I really don't think they were, but there were more women and more people of color around than I think it would really surprise us. My husband and I were watching a Doctor Who episode that was taking place in London in the 1600s, and they had Black people walking around. And Andrew said, that's modern. That's not real. And so we did some research. It turns out there were lots and lots of people of color, free people of color, living in London at the time. One of the most talked about musicians in Henry VIII's court was a Black man. The person that actually made it to the North Pole first was a Black man, an African American. These are not misrepresentations. This is just going back through the records and realizing what we missed. And the last one was, there's a new exhibit at the American Museum of Natural History about Matthew Henderson, who was the lead guide for the Perry expedition that went to the pole, and he's the person that actually was at the pole first. So there's a whole hidden history. We were never just left out of society entirely. I mean, there's so much that was left out of the writing of history.
Well, they say that history is written by the victors.
Yeah.
So if you've got, you kind of change that around. If history is written by white males, then they're going to only talk about white males.
Yeah. And again, these are good people. These are not bad people. I mean, I asked my husband, who went to Oxford, and I saw pictures of his astronomy group, and there aren't any women there. And I said to him, did it ever occur to you? Did you ever ask the question, where are people of color? Where are women? And he said, no, he just never, this wonderful person, he just thought, well, this is what astronomers are, that we must be the only people that like astronomy. And that's not true. So, I mean, this is not going to be perfect, figuring out, sending people of color and a woman around the moon. And, I mean, everybody's going to be offended, I think, somehow, but we're trying, and we have a lot of space to catch up. So, I mean, at NASA, we are trying to curate diversity, as much as we can.
Michelle, believe it or not, we've only got a few more minutes. I know. It just, you just fascinate us so much that we're just totally enthralled. I think you have this I think you have what is known in the Atlantean world as a storyteller voice.
Oh, thank you. I
just-
love storytelling. Yeah, thank you.
With your
That's a
stories.
big compliment. Yeah.
Do you have any parting thoughts for us? So what is the next thing that we really need to get excited about?
Oh, wow. I mean, there's science fiction, I think that, we're about to go, I think I said the same thing last year. Modern physics continues to show us that what we think reality is not. I mean, it's basically at the scale that we are, we're not really aware of all of these little kind of waves of reality and probability just kind of juxtapositioning over each other. And that's what we are. The idea now that space and time are not really intrinsic parts of the universe the way we understand them. Just let your imaginations go wild, because I mean, we're losing hold on the idea that atoms are not made of little balls orbiting each other. That's not what an atom is at all. It's all of these energy fluctuations and waves. Asking yourself questions: where could you get a silicon-based life form, or what might that be like? Or are we really missing something in the early universe? I mean, one of the things that we are kind of looking at each other when we see these big black holes that formed so soon. Is there another way the universe can form black holes that we don't know about? We're thinking about that.
Aren't the black
Well,
holes?
I know you mentioned, you're not only looking for life on planets, you're also looking for technology, and
Yes.
technology almost always equates to life.
Oh yeah, no, that's the intent. Yeah, that if we find something, if we find a planet with chemicals that look like pollution in its atmosphere, the thing that I think is somewhat likely relatively soon. I mean, no guarantee, but we're now able to read using those fingerprints of light. We're able to read the chemistry of atmospheres around other stars. Webb is sensitive enough to do that. And we now are finding planets with water and oxygen and this and that. And we haven't found anything that's exactly like the Earth yet. But if we find something with water vapor, carbon dioxide, oxygen, and methane, those four things are very hard to get without life. Oxygen and methane destroy each other. It's one of the ways we form ozone, by the way. Oxygen and methane can't exist in an atmosphere for long. They'll break each other down. So if there's oxygen and methane, something is putting more oxygen and methane up. So I think that, probably, the first thing we're going to find is a planet where we can't say 100% that there is life there, but we can say that given the chemistry, we don't know how there could not be. That'll be frustrating because it's not like we know for sure, but we'll be able to look at a planet, or at least the star that the planet is around in the sky, and say there's most likely life there. And I think that has every possibility of happening in the next decade.
Aliens.
Because even if it's plants,
Exactly. I mean, it could just be algae, right? I mean, but I mean, algae produces methane, oxygen, carbon dioxide, water vapor. Yeah. So I mean, it's not that we're saying that there are dinosaurs or space aliens, but I think we can say there's somewhere else there's life, and I think that will happen soon. Yeah.
so cool. Thank you so much, Michelle. This has been so cool. It's just every time you come, you give us so much food for thought.
Yeah, find out more about neutron stars. We're doing crazy observations. I mean, a big ball that you can see in back of as well as in front of, because it's 2 times the mass of the sun. And these fuckers are real. I mean, I'm sorry, but they're amazing. It's amazing that they're real. Yeah.
Okay.
Michelle, what I will do, since we don't always keep the chats, I'm going to send you an email real quick with our Discord server for this year.
Sure.
And then you can put all kinds of stuff in there if you want to.
Like
Sounds
if you
good.
have any links you want to put there, it'll be permanently there. So that's
Okay, I will absolutely. I'll give you some movies about neutron stars. I'll give you movies about the big black holes early in the universe, all of that. So I'll do that.
Thank you so much.
Okay, thank you.
Thank you. Have a good
So
day.
good. Thank you.
Thank
Take
you.
care,
Thank
Michelle.
you.
Thank you so much.